So, this is our last video for this particular chapter. It's all about catalysis. Catalysis. A catalyst is a substance that increases the rate of a reaction without itself being consumed. How does it do it? Well, according to Arrhenius, K is equal to A, the frequency factor, times E raised to the minus EA over RT power. What the catalyst does is it lowers the activation energy. That's the job of a catalyst. That's how a catalyst does, and that's how it increases the rate of the reaction. It lowers the activation energy. So therefore, by lowering the activation energy, the value of K goes up. And as the value of K goes up, the reaction goes faster. Because as you know, the rate is equal to K times the concentrations of the reactants raised to the appropriate power, determined either 1 by the mechanism or 2 experimentally. And so we can see in this particular reaction that the activation energy is quite large here if we don't add a catalyst, and when it is catalyzed, when we do add a catalyst, we can see that the activation energy hill has gotten much smaller, which seems to make sense. I mean, in terms of thinking about collisions, remember, collisions and collision frequency are what necessary in order for us to determine the rate of the reaction. Of course, it's not just how often the molecules collide, but of course the energy associated with those collisions. Now, if it requires less energy in order to begin breaking those bonds, if it takes less energy, if the energy barrier hill is smaller, then more collisions that occur will have a sufficient amount of energy because there's less energy required to begin the reaction. And therefore, the reaction will be faster, strictly from the standpoint of looking at the collisions. Mathematically speaking, of course, as we said, if EA gets bigger, then K gets smaller, and therefore the reaction is faster. There's also such thing as a dog list. A dog list also speeds up the rate of reaction. Guess how? Guess. Everybody guess? Did you take a guess? Have you guessed yet? Oh, wait. Okay, I'll tell you. A dog list speeds up the rate of reaction by chasing the catalyst. I know you'd like that one. Rate catalyzed is greater than the rate uncatalyzed. EA for the catalyzed is less than EA of the uncatalyzed. Some catalysts, are heterogeneous. In heterogeneous catalysis, the reactions and the catalysts are in different phases, like the Haber synthesis of ammonia and the Ostwald process for the production of nitric acid. Of course, I know you're familiar with both of those. Catalytic converters, which you might be somewhat familiar with, especially if you're a person who likes cars. In homogeneous catalysts, or catalysis, the reactants and the catalyst are dispersed in a single phase, usually a liquid, like acid catalysis and base catalysis. The Haber process. The Haber process is the process in which we make ammonia from NH3. We use this catalyst here. This is a heterogeneous process because the nitrogen and the hydrogen are in the gaseous state, and the catalyst is a solid metal. And basically how it works, I'm going to give you a very, very basic idea of how it works. Catalysis itself is a science unto itself within chemistry. But the molecules come and they lay on top of the surface of the catalyst. Here, they kind of stick to the catalyst in a sense, and while they stick to the catalyst, it lowers the activation energy necessary to begin to break the bonds. And so it's much easier for the bonds to break, less energy is required, and on the surface of the catalyst, the bonds actually do break, the molecules or the correct atoms migrate together and reform the substances, the new substances, the products with new bonds, and then leave the catalyst. So this particular catalyst acts as a surface on which the reaction takes place on, and as it adheres to the surface, it lowers the activation energy of the process. So here's the process, and here's the catalyst. The Ostwald process is the process in which ammonia and oxygen react to form NO and H2O. They use a platinum rhodium catalyst in the Ostwald process. Then the NO is used to make NO2 in the following reaction. And then the NO2 is reacted with water and used to form nitrous acid and nitric acid. So this is the 3 steps in the Ostwald process, using platinum catalyst and platinum wire as a catalyst. Catalytic converters. There's a catalytic converter in your car right here. See, there's your engine. I don't know why it's out of your car, but let's put it back in your car when we're done. And there is the exhaust, and there's the exhaust pipe, and here are 2 converters. Okay? Converters, catalytic converters, usually contain metals like platinum and palladium, and their job is to get rid of stuff that we don't really want going into the atmosphere, like carbon monoxide and unburned hydrocarbons. So in your catalytic converter, carbon monoxide and unburned hydrocarbons react with oxygen to form carbon dioxide in water, because it's better to have carbon dioxide and water going into our atmosphere than it is carbon monoxide and unburned hydrocarbons. Also, catalytic converters take nitrogen oxides, which are not good in the atmosphere, and react them, and they kick out nitrogen and oxygen instead, which of course are better for the atmosphere. This, my friends, is a biological catalysis that's taking place, enzymatic catalysis. Here is our enzyme. An enzyme is basically a protein, and this protein has a particular shape, and this molecule is called the substrate. This molecule now is the enzyme. The substrate fits inside the enzyme, like basically it's been described as a lock fitting in or a key fitting in a lock, and only molecules with this shape will actually fit in this enzyme. So this enzyme, like most enzymes, is very specific as to what it works on. And now the enzyme and the substrate, they come together and they form this complex, and then what happens is that the substrate will now break apart into 2 new smaller molecules, leaving the enzyme behind. And so here's an example of that process. And in an uncatalyzed situation, potential energy, you've got your substrate, you got your products. In a catalyzed situation with your enzyme and your substrate work together. They go over the energy barrier, the activation hill, and then they form the intermediate, which is the enzyme and substrate complex, and then they have to go up the energy hill again and then form the the enzyme again and the product. So we see that the enzyme starts out as a reactant, ends up as a product, and like all catalysts, is not used up in the reaction. And that's the end of the show. Don't worry about those last things that we just showed you about. One thing that he doesn't mention in these slides is that there are other types of catalysts, the ones that generally are homogeneous. Well, they become part of the mechanism, and we'll spend a little time talking about that tomorrow in class. Have a good day.